Do you feel like a coffee break? So do I. What about we talk about the design of your equals method? Methods that you use all the time, even when you don't know it, and that you never write yourself. First, because it's boring, and second, because your IDE can do it for you. Is your IDE good at generating this method? Are there better patterns of code than the one it gives you? These are the questions I would like to answer in this JEP Café. So you will learn about performance, instance checking, pattern matching for instance of, predictive branching, all these good things with JMH benchmarks that, once again, will help you design simple and performant equals methods. The equals and the hashCode methods are probably the first methods you learn to generate in your IDE, along with the toString method, of course. And don't get me wrong, generating them is a good thing, especially for the hashCode method, because writing a good hashCode method is actually not that easy. And because it is used in places where you may not expect it, a bad hashCode implementation can lead to major performance hits in your application. So yes, you should definitely use this generated hashCode method, unless you know what you are doing. I just would like to start with the first example to show you what could go wrong with a dumb hashCode implementation. And when I said dumb, suppose you have a point record, plain and simple. You do not touch this class, so the hashCode implementation is provided by the JDK. Good. And then let us write this completely dumb implementation of a hashCode method that always returns 0. I know, it's completely stupid, never do that in your application. But this implementation is actually okay with the spec. 2 points that are equal do have the same hashCode. Let us try to put these points in a hash set along with the following code. And by the way, we are using this factory method, new hash set, that was added in Java 19, so that you can use in 21. It creates a large enough hash set to hold all your values without having to resize it on the fly. Neat. I love this one. So let us measure the time it takes to run this code. In both cases, the point with the default hashCode implementation and the dumb point that has this stupid one. And as you can see, the performance hit is quite hard. That's a factor of 20 between a good hashCode and a stupid hashCode. Why is that? Well, as you probably know, a hash set is actually wrapping a hash map. And the hash map first computes the hashCode of your key to decide in which bucket it will store your entry. If all the hashcodes are the same, then you will get collisions, leading to the construction of a linked list that will become a red-black tree if this list is too long. This is a code that is much more complex and costly to run than the simple storing of an entry in an array, thus the performance hit. So I hope this example convinced you. If you're using records, do not touch anything. And for your plain classes, let your IDE generate your hashCode method for you. It's much safer most of the time. Let us go back to our initial subject and talk about the equals method. There is actually a number of generators that you can use, and I would like to first take a look at the code they give you to compare these patterns. In all the rest, we are going to use our good friend the record point with two components, x and y, of type int. This is a very simple example, and comparing two instances of this record is quite fast. It's only about comparing two int values, which is, yes, fast. You may have objects in your application with a more complex state that will be more costly to compare. First, we have the default generators of the Eclipse IDE and the IntelliJ IDE, which are slightly different. Here is the generated code by both of them, and as you can see, it's mostly the same, organized in a different way. It starts with the comparison of this and other with equal, to quickly exit if the objects are actually the same. This is an instance check and is seen as an optimization that almost all the generators are using. Then it compares the classes, also with equal, because you know that there is only one instance of a given class in your application. And then the cast and the comparison of the internal state of your objects. Then you can also use the Guava generator, which is also very similar, just organized in a different way. And you can see that all these generated code compare the instances with equal, then the classes, then they do a cast and compare the internal state of your objects. And then you can check the Apache Commons Long 3 generator. The code is organized in the same way. First compare the instances, then the class, and then the internal state of your object, but this time using a builder. On the one hand, I find this code nice and readable, but on the other hand, I suspect that it will not be great performance-wise. Creating this builder is costly, much more costly than comparing primitive types with equal. If performance is not an issue for you, and you want to favor the readability of your code, this is definitely a solution that you can consider. Other than that, I'm not sure that this solution is very interesting. And because we also need to check your basic 101 equals method, we are going to add a plain instance of to the lot, and the same with this instance check optimization first. And because this is Java 21, we are going to add two more. First, the plain equals method that is present in your records. You do not see this implementation because it is added for you by the compiler, but it's still there. And then the implementation advertised in the JEP about pattern matching for instance of. This is the JEP 394, delivered in the JDK 16 and written by Gavin Bierman. We can take a look at this implementation now because it's really interesting. As you can see, there is one major difference between this implementation and all the others, including, by the way, the default implementation you currently get when you create a record, which is it does not check if the instances are the same or not with equal. And it does not check if the classes are the same or not neither. It directly checks for the pattern. Could this be a mistake? A missing optimization overlooked by Gavin Bierman that wrote the JEP? Or is it actually the right way to write your equals method? So let us add this method from the JEP and also modify it by adding this instance check before to see if this is an optimization or not. And by the way, we are going to use the record pattern because this is what we have in 21 and because our point class is a record. The most important question is this instance check with equal an optimization or not? And if it is really an optimization, why does the code in the JEP doesn't use it? Why will it give up on what looks like an obvious optimization? Well, you know the drill, right? When it comes to performance, there is only one principle to follow: measure, don't guess. Before we move on and examine all this, I would like to talk about a very important point in computing, which is called predictive branching. You may be wondering why we are talking about that now. In fact, it turns out that it actually plays a key role in all this. So we are going to spend a few minutes to explain what it is. Predictive branching is a nifty feature that may make the execution of your tests much faster. It's not that it doesn't execute your test, because it does. It needs to execute it. It's more that it makes a bet on the outcome of this test, starts to execute one of the branch of your if statement, and if the bet is a win, carries on with your code. Which is great, because if it works, then it can execute your code much faster. But if it doesn't, then it becomes a performance hit, because it needs to roll back what it did and take the other branch. So let us see some benches on this topic. First, let us run this code. We are just summing all the int values of an array of size 400. There is no test in it, and it runs in about 72 nanoseconds on my machine. Then we are going to suppose that all the elements of this array are even integers, and we just add a test on that, and note that the result of this test is always true. This gives us an idea of the cost of testing each element. On the overall, running this code takes 110 nanoseconds on my machine, which is about 50% more than not running the test. Now we are going to run 3 more benches to evaluate the cost of a failing test. Let us make the last element of this array an odd integer. So the last test of the series is failing when all the other tests are a success. And you can see that having just one test that is failing when all the others are successful is actually quite costly. You could expect that the performance should be the same because it's the same test, just a different outcome. And we are executing 400 tests in 110 nanoseconds, so the throughput of this code is about 0.27 nanosecond per operation. But because the result is not what the optimizer expected, the performance hit for the single failing test is about 7 nanoseconds, which is quite a big performance hit. This single failing test is about 30 times slower than all the others. This is the cost of a failing predictive branching. Now, let us move this failing test from the end of the array to the middle of the array. And you can see that the performance hit this time is almost doubled. It is now about 13 nanoseconds instead of 7. It looks like we are paying for the transition from one state to the other. The first state being the expected outcome of the next test is true, and the second state being the expected outcome is false. We can see that by running the same bench with 2 consecutive odd integers at the middle of the array instead of 1. If we measure this performance, we can see that it is the same as the one where we have only 1 odd integer, about 123 nanoseconds. That confirms it. What is costly is to fail the predictive branching optimization, that is, to transition from one state to the other. Now we can try one last test, having 2 odd integers spread apart in our array, one at the first third and another one at the second third. And you can see that the performance hit this time is even higher. Not as high as expected. If we were paying for transitions, the performance hit would have been 138 nanoseconds, and it's only 128, but still higher than having 2 odd consecutive integers. So this gives you an idea of the cost of having a test with an outcome that is not what this predictive branching feature would have expected. Actually testing elements and having an outcome that is completely random is costly. You should try to avoid being in such a situation when you can. Now the question is, how is this related to the design of your equals method? Well, bear with me, this is what you are going to see right now. How can we see if predictive branching has an impact on the performance of an equals method? Well, there is only one way to find out. Create the right set of data and run all the equals method we have on it. All the use cases we are going to see are the same. We have a list of 400 point instances, point being the record we created earlier. We just loop over this list and check if a given object is equal to the objects of this list. This is the code we are running on different sets of data. And by the way, this black hole object is given to you by JMH, and you can use it to make sure that all the steps of your computation are actually executed, and that hotspot will not optimize things and remove some of your code because it finds that it's actually useless, which is always the case when you are running benchmarks. You absolutely want to avoid that situation. This black hole trick is very useful for that. The first use case runs on a list of points that are all the same instance of the point record. So yes, they are all the same object. I'm not sure that you will see that a lot in your applications, but we need to start somewhere. And you can see that the result is what we expected. All the methods that first checked for the instance equality perform better, and the pattern matching one is lagging behind. So in that case, performing this instance check is a good idea. You will get better performance. Let us move on to our next use case. We now have a list of objects, still 400, and this time they are all different instances, but they are all carrying the same state. So they are all equal. And the object used for the comparison is also equal to all of them, but a different instance. All the calls to this equal are now false. The class comparisons are true, so all the methods are executing the code that is comparing the internal state of the objects. And because the state is the same, they have to execute all the instructions of this state comparison. And this time the result is different. The commons long pattern is lagging behind, as expected. Obviously, the goal of the design proposed by commons long is not performance, but readability, which is perfectly okay. And all the others are doing roughly the same. But what's interesting is two things. First, using a simple pattern matching without this instance check before actually performs better than the rest, by about 40%, which is significant. And even if you compare the plain instance of with pattern matching, you can see that it is slower by about 10%, which is also significant. So pattern matching is actually doing very well in that situation. And because neither instance of nor the pattern matching solutions are executing the instance check, they save on this test, which is executed by all the others. So in the case of a list of objects that are different but that carry the same state, calling this instance check does not optimize anything, it is actually a performance hit. For the next use case, we are going to use a list of objects of the same type, once again, but this time they are all different, and the object we compare is also different. We expect a result that is similar to the previous one. The instance check is always false, the class check is always true, so the optimization there is in fact an overhead. And indeed, the results are similar. There is one result that is interesting in this table, which is the instance of versus the pattern matching one. Instance of is better with 142 nanoseconds, and pattern matching is behind with 178 nanoseconds. You may be wondering why the result is different. Well, we are using a record pattern in this bench that creates the two pattern variables x and y by calling the accessors of this record. These accessors need to be called to create the pattern variables because there may be some code in that needs to be executed, like a defensive copy, for instance. So not calling the accessors would actually be a backdoor to access the internal state carried by your records without any security checks or validations. Then we use X for the comparison, that is failing, so Y is actually not used. When you're just checking for the type with instance of, no pattern variable is created. You create them lazily. And in that case, you create X and not Y. So in the case where you have accessors that are costly to execute, using a plain type pattern instead of a record pattern may actually be more efficient. For the last use case of this first series, we are going to use a list of other objects of a different type. So the instance check is always false, the class check is also always false, and the rest of the code is not executed. So on the one hand, we are executing this code, and on the other hand, the instance of is also always false, and the pattern variables are not created. So which one will perform better? Well, the benches give us a clear win for pattern matching with a factor of almost 2. 180 nanoseconds for the instance check solutions and 95 nanoseconds for the pattern matching and instance of ones. Checking for the instance equality is always false, so it's an overhead. Adding the check for the class equality makes it more expensive than calling instance of or using pattern matching. And as we can expect, adding this instance check before executing an instance of or a pattern matching actually degrades your performance instead of improving them. At this point, you can see that there is only one use case where conducting an instance check is an optimization, which is you are comparing objects that are all the same instance. I'm not sure that this is the most common use case you'll come across in your applications. But so far, we haven't seen any predictive branching hit because all the tests had the same result. Now, what we're going to do is take these datasets again and add some glitches in them, objects that are different, to see the results. So let us take a look at the variations. We are going to check more use cases, still with a list of 400 elements, but we are going to add different objects in it, glitches, to trigger failures in a predictive branching algorithm. What is a glitch? Well, in a list where all the elements are the same as the one you compare them to, a glitch is a different object, and in a list where all the elements are different, a glitch is an element that is the same. Is it the same instance, or does it just carry the same state? Well, we need to check both, and this is what we are going to do. How are we going to distribute these glitches in a list? We are going to distribute them evenly, in the middle of the list. No glitch at the beginning, nor at the end. So one glitch makes it in the middle, two glitches are a 1/3 and 2/3, and 10 glitches, well, it looks like that. Now, the use cases we are going to consider are the following. First use case, a list with objects that are all the same instance, and a glitch is a different object of the same type. Second use case, a list with objects that are all different instances, but carrying the same state, so they are all equal. And a glitch is also an object that is different and of the same type. Third case, we are going to put different objects in your list of the same type, and we're going to add two different kinds of glitches. First, an object that is the same instance, and second, an object that is equal but a different instance. And the last case is the same, but with a list that contains objects of different types. That makes 4 use cases to look at, with 2 variations for 2 of them. When you have a list with instances that are all the same, adding glitches just makes the situation even worse for pattern matching. Checking for the instance gives you the result immediately, and even if the glitches degrade the performance, it is still much better than not doing it. So that situation is a clear win for all the solutions that are doing the instance check. Now the real question is, do you see this use case very often in your applications? Well, I'm not so sure. In the next use case, the instances are all different but equal, and the glitch is a different object of the same type. Pattern matching was performing better with no glitch, and it is still the case even if processing this data takes a little longer. This use case is a win for pattern matching and plain instance of. What I find interesting in this bench is that you can very clearly see that adding an instance check on the pattern matching or the plain instance of solutions actually degrades your performance. You may be thinking that this simple instance check is almost free. Well, clearly it's not. In the next two series, we have a list with objects of the same type but different, and in this one the glitch is an object that is always the same instance, and the same instance as the object we check it against. That should favor the solutions that are doing the instance checks, right? Well, it does not, and the reason is that predictive branching is messing up with this. On the one hand, you have an instance check that is mostly failing, and sometimes it's a success. And you saw on the predictive branching example that this is a situation that you do not want to find yourself into. And on the other hand, you have a pattern matching or an instance of with a type check somewhere that is never failing, a situation that is much better. So in this series, where you may be thinking that doing the instance check would be an optimization, it is actually something that, once again, degrades your performance. And if you check the pattern matching on instance of lines and compare them with the same solution with an instance check, you can see that doing this instance check is, again, a performance hit by a factor of about 50%. The following series is the same as the previous one. The only difference is that the glitch is a different instance that carries the same state. That is an object that is equal. The most interesting thing is that if you compare these numbers with the previous series, you can see that the instance check solutions are actually performing better, which may seem unexpected because this instance check is always failing in this series. Well, it's better because predictive branching is playing with you in this case, and it was playing against you in the previous one. The performance of pattern matching on plain instance of is the same as the previous series, which is also expected, and much better than all the other solutions by more than 50%. And the degradation due to the instance check is also roughly the same on pattern matching and the plain instance of solutions. The last two series are about comparing objects of different types with a glitch that is the same object and then a different object that is equal. So for this first case, the instance check is mostly failing and sometimes a success, which is not good. Pattern matching is mostly performing better, and adding an instance check is always a degradation of your performance. When the amount of glitches becomes higher, some solutions are doing better than pattern matching, that is slowly degrading over time, but actually up to a certain point. Be careful, because if you continue to increase the amount of glitches, pattern matching and plain instance of are actually performing better again. So just be aware of that and carefully bench your application with the actual data you are working on. And the last series is the same as the previous one, but instead of having an identical instance, the instances are different, still carrying the same state. It does not make much difference. The results are roughly the same as the previous series. The biggest difference is actually the degradation of the record case. And once again, you can see that adding the instance check degrades the performance for both pattern matching and instance of. That becomes better again as the number of glitches increases. So what can you make of all this? how all this can help you write a better code. If there is one conclusion you should draw, it is the following: measure, don't guess. You saw that there are many cases where checking for the instance of an object actually degrades your performances. It's actually what is happening in most of the cases I showed you. But as usual, choosing the right solution is really about understanding what are your most common use cases, what kind of object are you comparing, are they all of the same type, are they all different, or sometimes you are comparing identical instances, what is the amount of failing tests you are expecting, are they mostly failing, mostly successful, or evenly balanced? In short, what is your application doing? How is it working? What kind of data are you processing? As a rule of thumb, in most of the cases I just showed you, doing this instance check is actually a performance hit. The only use case we saw where it is performing better is when all your objects are the same instance. In all the others, not doing it is probably your best bet. Should you rely on the code your IDE can generate for you? Well, to be honest, I have mixed feelings about it. These patterns haven't changed much in years, like 15 years, maybe even more. And what was true performance-wise 15, 20 years ago might have changed now. Maybe thinking about these patterns of code again could be a good idea. But if you're lucky enough to have an application running on Java 21, pattern matching is definitely your best choice. If you have complex accessors, type pattern is probably your best choice, and if not, record pattern will give you a simpler solution with a more readable code and very good performance-wise. And with this, I'm out of coffee, so that's it for today. Talk to you soon.